radioactive decay and half-life. So radioactive decay is when an unstable atom, a nuclei, because it's all about the nucleus, changes to become a stable nuclei. It's totally random when this happens. There's no way of speeding it up or slowing it down. Now the number of those nuclei that change from unstable to stable is so the number of decays per second is called the activity. The unit of activity is the becquerel, BQ. So 1 BQ equals 1 decay per second. So activity is also sometimes measured in counts per minute. So that's how many decays happened in 1 minute. We can measure decay in something called half-life. So half-life is the time it takes for the amount of radioactive nuclei we've got to go down by half. So for instance, if we started with 12, then after 1 half-life, we'd have 6 unstable nuclei left. If we waited another half-life, we'd have 3 unstable nuclei left. So it wouldn't go down by 6 each time, it goes down by half of however many you've got. So if we've got 6, it goes down by 3. If we've got 12, it goes down by 6, and so on. So half-life is also the amount of time for the activity to go down by half. So if we started with an activity of 100, after 1 half-life we'd have an activity of 50, and after 2 half-lives we'd have an activity of 25. So the half-life of uranium 235 is 700 million years. If you've got a 2 kilogram block of uranium, how much is left 1400 million years later? So after the first 700 million years, the 2 kilograms is going to be split in half, so you've only got 1 kilogram of radioactive uranium left. The other kilogram will now be stable uranium. If we wait another 700 million years, another half-life, so that now we've waited 1400 million years, then that 1 kilogram half of it will have decayed, and so we'll have 500 grams, half a kilogram left that's still radioactive. Equally, if the activity starts at 100 becquerels and takes 2 hours to go down to 25 becquerels, what's the half-life? So we can see that if we had an activity of 100 and then we chop it in half, we'll have an activity of 50. If we chop it in half again, we'll have an activity of 25. So we've had to wait 2 half-lives for it to go down, and that took 2 hours. So that means 1 half-life was 1 hour. So radioactive decay is totally random. Nothing you can do to speed it up or slow it down. Heating or cooling a sample doesn't change the amount of radioactivity that we've got. Let's call n subscript 0 the starting amount of a radioactive substance we've got. So for instance, n0 could be 1.2 kilograms or 3.4 kilograms or whatever the amount that we've got starting. Then the amount of radioactive material we have at some time t later, let's call that n brackets t. So n brackets t stands for n as a function of time. So we want to know how much radioactive substance we've got as a function of time. And it's going to be given by this exponential decay equation. So the amount of radioactive substance at any given time t is going to be the amount we started with, n0, times the exponential of minus lambda times t, where t is the time and lambda is a constant called the decay constant, which will be different for every different radioactive substance. So every radioactive substance decays exponentially, but the precise speed at which it decays depends on the nature of the substance that we've got. E stands for the exponential, so E is just a number, 2.71. The units of the decay constant are going to be inverse seconds. So for example, if we start with 3 kilograms of a radioactive substance and the decay constant is 0.12 inverse seconds, how much is left after 3.2 seconds? So if we plug those numbers into our decay equation, First of all, we need to times 0.12 by 3.2, the decay constant times the time. Then we times that by -1 and we take the exponential of it. Then we times that by the amount we started with, 3 kilograms. And we can see that at 3.2 seconds, the amount that we're going to have left is 2.04 kilograms. We can also do calculations using molar mass. So remember, the number of atoms in a sample is the number of moles in the sample times Avogadro's constant. So for example, if we've got 12 grams of an isotope, the decay constant is 2.87 times 10 to the minus 5 inverse seconds. The molar mass of that isotope is 234 grams per mole. How many atoms are in the sample 3 minutes ago? So 3 minutes is 3 times 60, so that's 180 seconds. The number of moles we've got is the mass of the sample divided by the molar mass. So that's going to give us 0.0512 moles. So the number of atoms we've got is going to be that times Avogadro's constant. Now we can plug that into our decay equation. So now that we know n, we can work out n0. So we need to divide by exponential minus lambda t, which is the same as timesing by exponential plus lambda t. So n0 is going to be 3.087 times 10 to the 22 times the exponential of 2.87 times 10 to the minus 5 times 180. So n0 is 3.1 times 10 to the 22. The activity is the minus the rate of change of the number of nuclei with respect to time. So if we've got some number of nuclei n, the activity is minus dn dt, the rate of change of n with respect to time. So our expression for n as a function of time is n0 exponential minus lambda t. If we differentiate that, then what we're going to have for activity is that the activity is lambda, our decay constant, times n0 e to the minus lambda t. But of course, that's just our expression for n, the number of radioactive nuclei we've got, as a function of t. So the activity is always the decay constant times the number of nuclei we've got at any given time. We can also rewrite that in the same form if we define our starting activity, A0, as lambda times the starting amount of radioactive substance, N0, then the activity is given as the activity at any given time is our starting activity times the exponential of minus the decay constant times the time. So if we think about time, we can imagine asking ourselves how long it is before we've got half of the substance left. So that, before we define that to be the half-life. So if we wait some amount of time, which is the half-life, which we'll call big T, then at time equals big T, n is going to be n0 over 2, because the amount of stuff that we've got left is half of what we originally started with. If we plug that into our equations and cancel for n0, and then take the inverse mathematical operation of an exponential, which is the natural logarithm, ln, then we can rearrange the algebra and find that the half-life is ln2, which is a number, just a constant, divided by the decay constant, which is a fixed number that changes depending on the nature of the substance that we've got. So 0.69 divided by the decay constant always equals the half-life in seconds. So for example, if we've got a radioactive isotope and it's got a decay constant of 2.3 times 10 to the minus 3 inverse seconds, we can find the half-life as ln2 divided by that, so 301 seconds. Now if we plot the amount of radioactive substance we've got as a graph, we can see that the counts per minute, the activity, or indeed the amount of radioactive substance is going to be an exponential decay like this. We can find the half-life, or the decay constant, by measuring at what point the activity or the amount of radioactive substance we've got has decayed down to half its value. So if we start at 80, we can draw across to the graph at 40. and then read down to find the time. Then, if we're going from 40 and we half that again, we're going to go to 20, and we can see the time that that took, and so on. And so we can use the graph to find the half-life of a radioactive substance. If you plot the natural logarithm of the amount of radioactive substance we've got against time, then you get a straight line. And the gradient of the line is going to be the decay constant. So recall that an isotope is an atom of the same element, so it's got the same number of protons, but it's got a different number of neutrons. So all isotopes of carbon are carbon because they've all got 6 protons, but they've got a different number of neutrons. So for instance, carbon 13 has 1 more neutron, carbon 14 has 2 more neutrons. Every living thing has carbon in it. Carbon 14 is a radioactive isotope. So carbon 14 decays and transmutes and turns into a different version into nitrogen 14. So it decays via beta decay, releasing an electron and an antineutrino. So living things are always adding new carbon to them from food and the environment. And some of that carbon that they take in is the radioactive isotope carbon 14. But when something dies, it stops adding new carbon. So when it dies, it has a fixed amount of the carbon 14. That means the amount of carbon 14 in the remains of an animal or a plant is going to decay over time because it's radioactive and it turns into the nitrogen. So the half-life of carbon 14 is 5,700 years. So if we measure the amount of carbon 14 that's left in something, we can work out how long ago it must have died. Now the limit of this technique, this carbon dating technique, is about 50,000 years. If something's older than that, we can't use carbon dating on it as there isn't enough carbon 14 left to get an accurate age. It also depends about assumptions about how much carbon 14 was in the atmosphere when a given animal or plant died.